Now we'll learn how to solve some problems on elasticity. Elasticity is a very easy chapter. Problems also are very easy. In fact, whole of physics is easy, right? So you've got a rod whose length is 1 meter. The area of cross section is 1.5 centimeter square. We are subjecting it to a force, a pull of 1.5 into 10 to the power 4 Newton. Young's modulus is given as 2 into 10 to the power 11 Newton per meter square. We have to find the change in length, delta L, the extension. So how to start? Always keep the basic equation in mind, right? Then you'll never get into errors. Y. What is Y? Stress by strain. What is stress? Force upon area. And what is strain? Delta L by L. So Y becomes, this L will go up, so you'll get F L by A delta L. And therefore, delta L becomes FL by AY, right? This is the formula for extension, delta L, FL by AY. So F is given 1.5 into 10 to the power 4 Newton. L is 1 meter. A is 1.5 centimeter square, so to convert to meter square, so we multiply by 10 to the power minus 4 meter square. And Young's modulus is 2 into 10 to the power 11 Newton per meter square. So this is the equation you've got. Now this 1.5 will kill this 1.5, right? This 10 to the power minus 4, 10 to the power 11 will give you 10 to the power 7. This 10 to the power 7 will go upstairs and become 10 to the power minus 3. And 1 by 2 will give us 0.5. So 0.5 into 10 to the power minus 3 meters. And that is 0.5 mm. Problem solved, right? So what is the question? Length of the rod was given 1 meter. Area of cross section was 1.5 centimeter square. The force applied on it was 1.5 into 10 to the power 4 Newton. The Young's modulus was given as 2 into 10 to the power 11 Newton per meter square. We have to find the extension delta L. So we use the formula for Young's modulus. Y equal to stress by strain. Stress is force upon area. Strain is delta L by L. So you got Y equal to FL by A delta L. And therefore delta L becomes FL by AY. And we put the values. We got the answer as 0.5 mm. Let us look at one easy question. Which of the following materials has got the maximum elasticity? Rubber, copper, glass, steel. Suppose you get this kind of question. Which of the following has got the maximum elasticity? Then you may think of rubber, right? But that is not correct. In the language of physics, elasticity is decided by Young's modulus. And Young's modulus is maximum for steel. So out of all this, rubber, copper, glass, steel has got maximum elasticity. Because Young's modulus is maximum for steel. Now let us look at one more problem. There is a rope which is hung from the ceiling. The density of the rope is 1.5 gram per centimeter cube. Young's modulus of the material of the rope is 5 into 10 to the power 6 Newton per meter square. The length of the rope is 8 meters. G is 10 meter per second square. Question is, what is the increase in length of the rope due to its own weight? So that is the question. Important thing to understand, whenever we hang something from the ceiling, the weight acts at midpoint, right? Therefore, in the formula for Young's modulus, we have to replace L by 2. So, what is the equation for Young's modulus? Young's modulus is stress by strain. stress is force upon area and strain is delta L by L. But here L will become L by 2. So let's write that here. So L by 2 if we write, then what do we get? This L will go up, so we'll get FL, and we get A delta L, 2A delta L in this case only. Otherwise it is FL by A delta L. So therefore, delta L is equal to FL by 2AY in this particular problem, right? So force is weight is mg, right? L is the length of the rope, which is 8 meters. A is the area of cross section that we don't have. We have got Young's modulus, which is equal to 5 into 10 to the power 6 Newton per meter square. Now we have got density. Density is what? Mass by volume, right? So we can write this as mg. We have got L here, 8. Then we multiply this by L, one more. So we get 2Al, which is the volume. So we multiply once more by L here. So we get 8 square and 5 into 10 to the power 6. Right? This mass by volume is density. So density becomes 1.5 gram per centimeter cube, that is 1500 kg per meter cube. This is m by Al. G is 10 and 8 square is 64 divided by 2 into 5 into 10 to the power 6. So what do we get? This is 10, so 10 to the power 7 here. This will go upstairs. So it will become 10 to the power minus 7. So you will get 10 to the power minus 4 here. And then you have to multiply this with 15. So what you will get? 15 into 4, 60. 15 into 6, 96. 15 into 6, 90. And then 6 there. So 96. So we get 9.6 into 10 to the power minus 2 meter. So this is how we solve this question. Right? So the density of the rope was given 1.5 gram per centimeter cube. Young's modulus was given 5 into 10 to the power 6 Newton per meter square. The length of the rope was 8 meters. G was 10 meter per second square. We had to find delta L. So use the formula y equal to F by A delta L by L. But here L became L by 2 because the weight acts at midpoint. So FL by 2A delta L. So from here we get delta L equal to FL by 2AY. So then we substituted the values and we got the answer as 9.6 into 10 to the power minus 2 meters. As simple as this. Now let us look at one more problem on elasticity. Two wires are there of the same material, right? Their lengths are in the ratio 1:2. And their diameters is in the ratio 2:1. If they are stretched with the same force, what is the ratio of their increase in length? So that is the question. So if diameters are in the ratio 2:1, what is the ratio of the radii? They will be in the same ratio because both will get divided by 2, right? So R1 is to R2 is also 2:1. That may be confusing for some people, but remember, if diameters are in the ratio 2:1, radii also will be in the ratio 2:1. Now, we know that Young's modulus is given by stress by strain, force upon area by delta L by L. So therefore, Y becomes FL by A delta L. And therefore, delta L is FL by AY. Now, in the case of the second wire, the length has become double. So, delta L dash will be equal to F into 2L. And area will become 4 times, because radius has become, basically area will become 1/4 times because radius has become half. R2 is half of R1. So then we get pi into R by 2 whole square into y. This was FL by pi R square y. So this 2 square we get here. So finally we realize that this is 8 times delta L. So delta L1 is to delta L2 will become 1:8, right? So this is the answer to this particular question. The question is, 2 wires of same material have their lengths in the ratio L1 is to L2 is equal to 1:2. Their diameters are the ratio 2:1. So D1 is to D2 is 2:1. So first thing we understood was R1 is to R2 is 2:1. Then Young's modulus is given by stress by strain F by A divided by delta L by L. So we get Y equal to FL by A delta L. Delta L becomes FL by AY. FL by pi R square Y. Delta L dash, that is delta L2, will be F. The length has become 2L. The radius has become half. So R by 2 we put it here. And we get 8 times delta L. Therefore delta L1 by delta L2 will be 1:8. Right? That's all. Now let us look at some simple problems on elasticity. Suppose a wire is having a length of capital L. We apply a force F on this and the length increases by, say, small l. The force applied is F. What is the energy stored? Right? What is the energy stored? That is equal to work done. So here in this case, the average force becomes F by 2. Right? Initially, we don't apply much force. As the length increases, the final force is F. So average force is F by 2. Therefore, the energy stored will become average force, that is F by 2, into the increase in length L. So this is the energy stored in this case. Right? Now let us look at one more question. Suppose the Young's modulus of a wire is Y. Okay. And say the strain that we get in that wire is, say, equal to epsilon naught. So epsilon is the strain, let us say. Y is Young's modulus. We have to find the energy stored per unit volume. Right? Young's modulus is given as Y. The strain is epsilon. So what is the energy stored per unit volume? Energy stored per unit volume. This is given by what formula? This is half stress into strain. Half stress into strain. What is stress? Stress is Y into strain, right? Y is stress by strain. So stress is Y into strain. So we get the formula as half into Y into strain square. So therefore this is equal to half Y epsilon square. So this is the energy stored per unit volume. So we looked at 2 simple questions right now. One wire was having a length L. Some force F was applied on that. The length increased by small l. So the energy stored in this situation will be average force into the increase in length. Average force is F by 2. So F by 2 into L gives us the energy stored. Here in this problem, we wanted to find out the energy stored per unit volume in terms of Young's modulus and strain. So energy per unit volume is given by half stress into strain, and stress is equal to Y into strain. Therefore, the energy stored per unit volume is half Y into strain square. Right? That's all. Now let us look at one problem where one wire is there and we hang a 20 Newton weight here. Right? So this is the force applied on the wire and the wire stretches by 1 millimeter, right? So this 20 Newton weight is hung here and this wire stretches by 1 millimeter. First question is, what is the energy stored? So energy stored will be equal to average force, right? Energy stored will be average force F by 2 into delta L. F is 20 Newton, so average will be 20 by 2, that is 10, and delta L is 1 millimeter, 1 into 10 to the power minus 3. And this will give us 0.01 joules. This is the energy stored in this process. And what is the loss in gravitational potential energy? Loss in gravitational potential energy will be equal to mgh. mg is 20 Newton. And this will also come down by 1 millimeter, so 1 into 10 to the power minus 3 meters, and we get 0.02 joules. So gravitational potential energy is lost, and that is equal to 0.02 joules. But the energy stored in the wire is only 0.01 joules. So what happened to the balance energy? Right? Understand this. A wire is there, 20 Newton weight is hung, the wire extends by 1 millimeter. So the energy stored in the wire is average force into change in length. Average force is F by 2 into delta L. F is 20 Newton divided by 2 multiplied by delta L. We get 0.01 joules. So this is the energy stored in the wire. The potential energy lost is given by mgh. M is 20, mg is 20 Newton, and h is again 1 millimeter, so we get 0.02 joules. So 0.02 joules of energy are lost, and the energy that is stored is only 0.01 joules. What happened to the balance energy? Yes, that energy will get dissipated as heat. So when this extends, the wire also will get some heated to some extent, and that energy will be lost. That's why the answers are different. Right? Energy stored is 0.01 joules, and the energy lost due to gravitation, loss in gravitational potential energy, is 0.02 joules.